Okay. And now, having computed the short circuit current gain, which is the maximum available current gain for your transistor, now we are going to see what happens if I'm going to connect a load to the collector of the transistor and I'm going to measure the gain. So in previous case, we were short circuiting this part, but now I'm connecting a load RL. I'm connecting a load RL across the collector and emitter terminal. Other things are going to be exactly same, and this voltage is going to be VCE, or I can say it is going to be V out also. You can say it's going to be V out or VCE. Current source is GM VB dash E. These things, resistance values and all will default, will come in your circuit RB B dash and RB dash E. This capacitance C B dash E will come. This capacitance C B dash C will come. That resistance R B dash C is very, very large. It is in the order of 4 mega ohms. We have seen in the very beginning of your hybrid 5 model, right? So I'm going to neglect the resistance R B dash E and RCE also. The two resistance I'm going to neglect. I'm going to have only these components only in my equivalent circuit. So I'm going to connect a resistive load in the output, and the simplified high frequency model is shown in the figure. So you can see this capacitance C B dash C is between the input and output of the circuit. So if you want to make the analysis even more simple, you can use Miller's theorem and decompose the C B dash C into two components, one here and one here. You can do that by using Miller's theorem. You can you can decompose this capacitance C B dash C into two capacitance, one at the input side and one at the output side. So Miller's theorem definition and formulas I have given in the first class. Please go through the definition and value for each component, how we are going to decompose that. So this will be the equivalent diagram. Okay, so you know that the impedance of the input side is reduced by 1 minus A. So Ci by 1 minus A. The percentage capacitor, it will be multiplied by 1 minus A. And A is going to be the voltage gain. So we have to find what is the voltage gain. Okay. And we have to find what is the voltage gain. The voltage gain equal to output by input. A capital A is equal to output by input. Output is VCE and input is VB dash E. Okay, so VCE by VB dash E. What is VCE? VCE is the voltage across RL. So this current GM VB dash E is going to flow like this in the circuit. So the polarity will be plus will be here. Okay, so depending on current flow only, you will have the polarity, right? So this terminal will correspond to plus and this terminal will correspond to minus. Okay, so since the polarity is going to change, you can, since the polarity is going to change, you can, then the polarity is going to change. You will get a minus sign. So minus GM into VB dash E into RL. So you know by Ohm's law, V is equal to IR. The current flowing through is going to be minus GM VB dash E, the opposite direction, into RL. Across load, I'm going to measure RL divided by the input is VB dash E. So VB dash E and VB dash E will get cancelled. So the gain will be equal to minus GM RL. And this minus sign is getting because in a common emitter amplifier, you have 180-degree phase shift between input and output. So because of that reason, you're getting this minus sign. So 1 minus A is going to be 1 minus of minus GMR. So you get 1 plus GM into R. Why we are finding this 1 minus A? Because of the input side, if you apply Miller's theorem, you will get Z by 1 minus A. Z is here, the capacitance. So capacitance, it is 1 by J omega C. So 1 by J omega C is multiplied by 1 plus GM RL. Because of that, you can see when you simplify at the input side, the capacitance will be multiplied by 1 plus GM into RL. So you will get CB dash C into 1 plus GM into RL. At the output side, you will not have this capacitance is not going to do any change. So I'm going to neglect the capacitance at the output side. Okay, both the input and output side, you will have the capacitance using Miller's theorem. But at the output side, it is not going to do any changes to my circuit. So I'm going to neglect that capacitance in the output side. Okay, so only at the input side, you get one capacitance in parallel additionally. You can see now the input has become separate, output has become separate by using Miller's theorem. Now I can analyze the circuit easily. Clear? So this capacitance CB dash C was present between the input and output, correct? So it was acting like a feedback capacitance. So that was making the analysis difficult. But now using Miller's theorem, I have decomposed the capacitance into one at the input and one at the output. So this is going to make my analysis very, very